Alright, so we're moving on to circular motion. Now it's really important to remember from last year and do a little bit of revision about what we learned last year. So hopefully this is not new to you, or at least is common sense to you. So the first thing to remember, circular motion is translational. There is no rotation happening around the centre of the object that is moving. The object instead is travelling in a straight line that is continuously changing, causing the curve effect of the circle. It requires an unbalanced force. The unbalanced force acts towards the centre of whatever the circle is. So this unbalanced force can be provided in a number of ways. It could be an object on a spring. So if you've ever played that game with the tennis ball on the peg and you hit it around, that's circular motion. Okay, the string is providing an inward acting force from its tension. You hit it sideways and it turns in a circle. It could be the friction between the tyres and the road. And a lot of the examples we're going to do are to do with cars and the road. And the reason for that is because we're going to talk about banking this year, why we can turn more quickly on a corner that's slightly elevated in an angle rather than as flat. And we're also going to look at aeroplanes and how aeroplanes do banked turns for the same reason. The unbalanced force always acts at a right angle to the velocity that the object has. So if we have a car moving along and the force acts at right angles to it, it's going to turn in a circle. Therefore, objects can change their direction, change their velocity without changing their speed. So you can be in a car and the speedometer continues to read a steady speed, but you're actually changing direction as you go around the corner. And for those of you who do drive, you'll know that if you just keep your foot on the accelerator at a steady rate as you're turning, you don't always keep a steady speed. So let's just remind ourselves of the two formulas we're going to use here. A equals b squared over r. The size of the acceleration that you get depends on how fast the object's going and how tight the turn is. If you look there, you can see that a very wide circle with a large r only generates a small need for the acceleration. So you don't have to apply much inward acting force to get that circular turn. On the other hand, if you want to turn in a very tight circle, r is very small, then you're going to need a much bigger acceleration. And this becomes important when we look here when we talk about F. So for an object to be able to turn in a circle, we must apply the force to it as an unbalanced force. It has to come from somewhere. If the force isn't big enough, then the object can't generate enough inward acceleration to make the turn safely, and the object will go flying off at a tangent in its straight line direction. So you can see here that this year, both R, V, and the mass are going to be more important when we're talking about can we achieve this turn safely? Do we have enough centripetal force available? You know, is there enough friction between the tyres and the road? What is the maximum speed that we can safely make this turn at? And those are the sort of questions that we're going to be answering about circular motion.